Alright, here come question 6. A copper wire with initial length 0.755 meter and cross-sectional area of 3.75 exponent -7 meter square is stretched until the strain in the wire is 0.015. Young modulus copper is 1.3 exponent 11 Pascal. Calculate the force applied and the strain energy. And later, yeah. Okay, so given the initial length, and this is a copper wire. So the Young modulus given. So this is the Y for copper, 1.3 exponent 11. Initial length given, cross-sectional area given, and stretch until the strain. This is the strain, epsilon. The strain has no unit. Find the force applied. Okay, so information given this one, yeah. L, area, strain, Young modulus. So how to find the force applied? So what can we do is, first we find the stress. We can find the stress from the Young modulus formula. Because we have the strain. We can find the stress, provided the Young modulus formula. Young modulus value. Okay, Young modulus is 1.3. So just substitute 1.3 exponent 11. And then stress over strain. Strain is 0.015. Okay, so what's my stress? My stress is 1.95 exponent 9. What's the unit? Pascal. Everything in SI unit because my Young modulus Pascal, so my stress also Pascal. Same unit as the Young modulus because this fella no unit. The strain has no unit. Okay, so now I have the stress. I can find the force applied in the wire. Copper wire. I have the cross-sectional area. Cross-section area already in meter square SI unit. Okay, so no harm. Okay, let's find out what's the force applied. I have the stress already. When I have the stress, I can find force. 1.95 exponent 9 Pascal SI unit. And then my area also in SI unit, meter square. So put inside, plug in the value. Yeah. Okay, so what's my force? My force is 731.25 Newton. Yes, that's my force. Force in the wire. Okay, force in the wire. Now, what's the strain energy in the wire? Oh, strain energy in the wire. So how to find? Strain energy in the wire is formula, half strain energy, U, equal to half Fe. Just now I got the force already, isn't it? I got the force already, 731. Okay, I don't have elongation, but what I have is the strain. I have the strain. This strain is what? Is elongation over length, original length. And this is the original length. Okay, so I need to find the elongation. Then I can do it. Yeah. Okay, let's find out my elongation. I have the strain 0.015. 0.015. My elongation over my initial length is 0.7755. 0.755. So what's my elongation? Okay, so 755. Okay, so let's calculate. My elongation is 0.011325 meter. Okay, put as many decimal places so that more accurate. So that's my elongation. I got the force already and elongation. So half force elongation, I get the strain energy. My force is 731.25. times with 0.011325. So what's the answer? 4.14 joule. Okay, that's the strain energy. So but right now, is everything correct? Yeah, my force is 731. Yes, correct. My strain energy 4.14. 4.14. That's right. 4.14 joule. 4.14 joule. That's correct. That's the strain energy stored in the wire. Okay. Now, if the cross-section area of the wire changes but the volume remains constant, remains the same, determine the fractional change in the cross-sectional area of the wire. Okay. Okay, now why the area of wire will change? Volume remain constant. Okay. It's because you stretch the wire, isn't it? Stretch the wire. The amount element in the wire still remain the same. That's why you say volume remains the same, but the area will change. How it change? Let's look at this diagram. This is how it change. This is the initial length before stretching, and the area is bigger, wider. After you stretch the wire, when the wire become longer, of course the area shrink. The area will shrink because you want to maintain the same volume. You want to maintain the same volume. That means the volume V1 must be equal to V2. Volume 1 must be equal to volume 2. So when the length increase, the area should shrink. Yeah, because you elongate, plus elongate, of course the area will shrink. Volume remain constant. That's it lah. Okay. So area will shrink. So volume remain constant. So V1 equal to V2. So remember the volume remain constant. So the length is stretched, but the area will shrink. Okay, remember that. So now I want to find the fractional change in the cross-sectional area. Fractional change in the cross-section area. That means what you want is the change in the area. The change in the area over is a fraction. You know, it's a fraction. That means it's a ratio. It's a fraction. That means the change divided by the original area. The change, fractional change in area means the change in the area divided by the original area. Okay, so that's how you get the fraction change in the area. So delta A over A naught. So what we need to do is we want to find the change in area. To find the change in area, you must find the final area. You must get the final area, A2. That's the final area. So I have the initial area. Yeah, initial area. This is the, actually this is the initial area. And this is the initial length, L1, A1. Okay, I put here. This is the initial area, initial length. So final length, L2, is actually initial length plus extension. So extension I got just now, 0.011325. So yeah, let's find out the final length. Final length is the initial length 0.755 plus the extension 0.011325. So which I get 0.766325 meter. That's the final length. So I can find the final area. Let's find out the final area. Let's do it. So 3.75 exponent -7 times the initial length 0.755 equal to the final area times 0.766325. Yes, I got the final length. So what's my final area? My final area is what's my final area? Final area is 3.6946 exponent -7 meter square. That's my final area. So once I got my final area, I can find my change in area. So what you want is this one lah. Delta A over A. That means final area minus initial area to get the change in area. This is the A2 minus A1 is the change in area. So let's find out. Okay. So yeah, A2 is 3.6946 exponent -7. Then minus with the initial area. Initial area is just 3.75 exponent -7. Yeah, the area string indeed. Yeah, you see, area 2 is less than area 1. It's string. You see, 3.75 and 3.69, the area string, while the length extend. Okay, the length plus e extend the area string. Okay, so let's find out the fraction change. So final area minus initial area, you get a change in area, divided by the original area. Original area is the 3.75 exponent -7. Okay, so what's the answer? The answer is -0.015. Yeah, that's the answer. So why is it negative? Negative because the area decreases when the wire is stretched. Okay, negative means the area decreases. Okay, so that's it. Very easy questions. Yeah, just apply all the formulas: Young modulus, stress, strain energy, strain, and remember when you stretch, always the length increase, but the area will decrease, will shrink. Volume normally is constant. Fraction change means it's a fraction, and on the top is the change in the area divided by the original value. Okay, when negative fraction change means it's decreasing, shows that something is decreasing. The negative shows something decreasing. Okay, that's all for these questions. See you again. Bye.